Hi, so welcome back. So we're now in chapter 3, NumPy. Well, to be honest with you, this is going to be a relatively short lecture for this video. Why? Because we have a lot less code blocks to go through. Okay, so without further ado, let me just go ahead with the content so that we can, quickly go through the important points and you need to know with the NumPy library so that you're better prepared for the upcoming test. Okay, so in this chapter we will learn how to use a library called NumPy, which is the most widely used tool to manage operations which involve arrays. Therefore, in this video, we will go through a quick introduction to NumPy, which will highlight the functions of the library that are most useful to, well, users like you and me, and then we will delve into certain practical examples with the examples provided from the textbook that uh, I have supplied you with. Well, it's not mine, but then I shared uh, the excerpts of the textbook that we're using this semester. Okay, anyway, so the NumPy library is something that does not come together with your uh, ordinary Python library, right? Because the built-in Python does not have the NumPy library, therefore you would have to install it using conda install NumPy and so on and so forth, right? So before we start off with this library and this chapter, you need to install the NumPy library first. Therefore, we could later on import the library NumPy and perform certain functions that are new to us. Okay, so what is NumPy library mainly used for? It's mainly used to create and edit arrays. So what is an array? It's a data structure which is quite similar to a list. However, the slight difference between a list and an array is actually it can contain only one type of object. Previously, in the previous lecture, in chapter 2, we can see that lists can comprise of a mixture of a list that contains floats, integers, strings, and inside the list you might even have a nested list, isn't it? However, in this particular chapter, we are dealing almost exclusively with arrays which are lists with only one type of object. Okay, so for example, we can have an array of integers, floats, strings, right? But we cannot have an array which has two or more data types at the very same time. Therefore, new users of NumPy library, you might ask, why are we using arrays instead of the typical lists, right? Because with arrays, the use of this type of data structure is faster, it has more functionalities, and, well, the book says it gives better representation of mathematical concepts. For example, vectors and matrices. Okay, so imagine you're dealing with so many numbers and a very huge data sets which comprise mostly of probably just integers or probably just floats, right? So imagine trying to process a huge volume of data, right? You would revert to the use of NumPy because NumPy handles these type of singular type of data very, very efficiently. Okay, so NumPy provides the user with a powerful object called ND array, aka also known as an array which expands the functionalities of Python. Okay, so first of all, we would like to import a library in Python. When we want to use an external library like NumPy, we need to import it before we can access its functionalities. Therefore, usually whenever you run something that is from an external library, please don't forget line number 2, right? This is crucial. Import NumPy as NP, because we are importing the library called NumPy, and we even created a nickname for it, which is NP, because you wouldn't want to call upon NumPy every single time and typing out NUMPY all the time. So instead of using NumPy, you can shorten it to NP, and you can call the NumPy as usual. Okay, like I said in the previous video, with Google Colab, the text editing is a little bit tricky, so please bear with the typing mistakes that you might see in this video. Okay, please bear with it. I won't make a lot of these mistakes, I promise. Okay, so like I said previously, before you can import the said library, you need to install it first. However, Jupyter has all the libraries that we need pre-installed. Okay, to do this, we need to open Jupyter, create a new Jupyter notebook, and write this code in this code block here with an empty cell and run it. Okay, so first of all, this is the first known step of running functions within a NumPy library is you need to import it first, right? So we import NumPy and assign NP to it. And line number 3 is we designate a variable called a, and then we are using the NumPy, the first known function to date between you and me, yes, the members of the class, is that in NumPy you have a function called zeros. And I mentioned previously, this does not have to adhere to the actual spelling of zeros, because zeros is usually spelled ZEROES, but then this is a logical programming language, so just type in 0 with an S at the end. So you will call upon something called a built-in method called zeros within NumPy. Okay, so after we create the zeros array within the NumPy library, we put a number in the parentheses, right? So this means if a single number is specified, it means that we are creating an array of one-dimensional type. Okay, so after creating the array called a, right, we print it out in line number 4. It takes an input of a tuple that specifies the dimensions of the array, and therefore after assigning a to the newly created zeros one-dimensional array, so we have 4 elements inside of the one-dimensional array using the NumPy library, we print it out, and then the result is actually, you've seen this here underneath, so it looks like this. We'll let it run for a bit. Okay, please tell me I have NumPy imported here, or else do I need to run NumPy in pip install? Gosh, I think so. Pip install NumPy in Google Colab. Oh, so it runs quite well. As you can see here, yes, it might take a while because we are importing NumPy as NP, so it's going to take some amount of time. Okay. Importing libraries within Google Colab. Because I don't really use Google Colab a lot, so I assume that's already installed, but it's okay. Import NumPy. Okay. For us to, okay, probably this is not within the textbook, but then actually if we import NumPy, oh, excuse me, when we import oh, why does it have to have doubles? It's okay. Import. This is pulling my leg, actually. Import NumPy. Right, underneath import NumPy, actually you can find out what is the version by typing in something called NumPy dot double underscore NumPy. This is really a challenge, so I'm very sorry. NumPy dot double underscore. Okay. NumPy version double underscore. Okay, so I have no idea why this is happening. Okay, so if you run this, let's see what happens. What it's going to return is actually it's going to return the version of NumPy that we have currently installed. What? NumPy dot version. Oh, because I have this one. I have an extra apparently I have an extra underscore down there, so yes. So actually this is what I wanted to show you. 1.19.5 is our current NumPy version. So apparently in this internet example that I have, it's in example, yeah, the version is 1.11.1. so wow, it's been a while. Okay, so this is actually the one of the most outdated versions of NumPy that we have seen. Okay, so after looking at how to identify the NumPy version and how to import the NumPy library and apply the first known built-in method inside of NumPy, which is zeros. Okay. Yeah, basically this and these are the same. It gives out the same. Yeah, it's 0.0.0.0 4 times. Because we want a 1D array with 4 elements. So from this point onwards, the examples written at rest for the rest of this chapter will need to be preceded or started off with import NumPy as NP. Okay, even though I don't really clearly state that you need to write import NumPy as NP for every single code block. Imagine that you would have to, yeah. So even if there's missing line of import NumPy as NP, I'll put it in. Don't worry. Okay, so just now we created a 1D array with 4 elements. Okay, so we can create NumPy arrays from lists and tuples with the function array, as shown in this code block below. Okay, so as usual, we import NumPy as NP, and the second built-in method inside of NumPy is actually the dot array function. So we pass the array function with inside. Yeah, we pass the array function a list of integers. So our integers are 1, 2, 3, 4. Okay, so that NumPy can create an array of integers. Okay, so let's see. Let us print out the A array first. See how this goes. Okay, so it shows you A is equal to 1, 2, 3, 4. Do you remember the previous chapter when we created a list 1, 2, 3, 4? Right? Since it's a list and it's not an array, you would find that actually if you just printed out this list 1, 2, 3, 4, you would have had the comma in between the numbers. However, if you're calling upon the array function inside of NumPy and you pass an array inside, and you pass a list inside the array, this is your newly created array. So in fact, the appearance of an array is actually slightly better than your garden variety list of integers 1, 2, 3, 4. Well, basically because we have removed the commas in between. Okay, so that's A, the first array. What about the second array? Okay, so for the second array, it's a little bit trickier. Why? Because we have a multi-dimensional list which contains both integers and floats. So this is something new to us also. So NumPy automatically converts the integer values to float because an array can logically contain only one type of data. So in other words, what I'm trying to tell you is that Python is an intelligent programming language in the sense that it tries to minimize errors whenever it can, right? Because if you did this in C++, definitely will throw up an error and then you're left trying to convert the integers to float, while Python does that automatically for you because it intelligently recognizes that, hey, we have a set of integers and we have a set of floats here. Why don't we convert the integers to floats, right? So this is what Python does internally. And then, yeah, that's the beauty of NumPy, actually. So by specifying a multi-dimensional list with both integers and floats, NumPy.array automatically converts it, and then you can see that the printout of the second array B is actually a thing of beauty, right? So you'll have 1 point, 2 point, and then 3.5 and 4.2. Notice you don't have a 0 at the end, but they just put a decimal point after the integer just to make sure that no error would come up, right? With the creation of the newly created array B. Okay, so that's that, creating arrays. We have the one-dimensional array, we have the multi-dimensional list with multi types of data, but then we learned that NumPy can automatically convert it so that there's no errors. Okay, so moving on, if you want to know the dimensions of an array that we need, but we want to populate its positions later, we want to pass in or assign certain values inside this placeholder positions later, we can create arrays of zeros or ones, right? So previously we had a one-dimensional array using the np.zeros, and we can also do the same thing with np.ones, O-N-E-S. So as we have seen previously, we created an array of zeros, but this time around in line 3, don't forget your import numpy as np. Like in line 3, you assign the variable a to consist of an array, to be an array which consists of 3 elements of a one-dimensional list, but all the elements are indeed zeros, right? So this is something new, line number 4. It's line number 3 because actually previously in the example in the book, this headliner here did not exist. I just added it so that we have a clear, so that we have a clear picture what the code block is about, right? So this code block is about creating arrays, continued from the previous code block. Okay, so in this line number 4, we use the new built-in method, which is called ones, right? So it's a bit unique. Why? Because we are passing inside a tuple 2, 3, which creates an array of ones with 2 lines and 3 columns. And we also specify the data type of the data in which we are generating the ones for. Is it integer, is it float? So here, not only did we specify the tuple, which tells Python to create a 2x3 array, but we are also telling Python that the data inside the newly created array is actually, it consists of integers. So when we create b, the integer is specified as a dtype, therefore b will contain only integer values. Okay, so not to ruin the surprise, but let's see what line number 8 does. So line number 8 is actually something that we've seen before. So you'll see 0, 0, 0. So this is an array of 3 zeros, right? Notice there is a slight difference. Since we're using NumPy dot zeros only and we did not specify the dot array function, notice that NumPy automatically recognizes the zeros, right, as an array. So the array consisting of 3 zeros are still separated with, as you can see here, commas, isn't it? Yep. So that's A. Let's go see what line number 9 does. Okay. So line number 9, when we run it, we will find that actually we have a 2x3. 1, 2, 3. 1, 2, 3. We have a 2x3 array consisting of ones, because it has here ones, and it doesn't have a decimal point thereafter. Why? Because we have specified the data type inside to be integer. So the beauty of zeros and ones is actually, upon further operation, you can actually fill in the element slots with your designated numbers. So these are what I call placeholders, and they're just temporary numbers before you proceed with your actual data. So this is basically just creating an empty, well, it's not really empty, it's a temporary array that you would modify later. Okay, so the functions ones and zeros, they take as inputs a tuple that specify the dimensions of the axes of the array. Okay, so not only can you specify the tuple 2, 3 for 1, so you can also do it for zeros. Yeah, so it takes a tuple, for example, this is our tuple 2, 3, which is actually the dimension of the axes of the array. So both zeros and ones can take additional parameter dtype or data type, right? So you can specify, is it a float, integer, and so on and so forth. To create an array that contains a sequence of numbers that goes from a starting value to an ending value, we can actually use another built-in function inside of NumPy, which is called linspace. This is actually called linear spacing. Yeah. So when you combine both words, when you concatenate both linear and spacing, so it becomes linspace. Therefore, you can see the use of linspace here in the following code block, right? So in this following code block, we import NumPy as NP as usual. So now we create a new array. It's called A. Yeah, I know A has been appearing since the beginning of this notebook, but please bear with me. So A takes a lot of changes in terms of its shape and sizes, right? So in this instance, A is actually linearly spaced. It starts from 1, it ends with 10, and we have 6. 1, 10, 6. What does this mean? Okay, so in linspace, this new method within NumPy that we're trying to learn is that the first one, you can see the syntax down here. Okay, so first we have the array name. Okay, np.linspace is the keyword that we use. We call upon the library NumPy, and we call upon the function linspace, and then you have 3 values that you have to identify, right? This is the start value, the end value, and the number of elements that you wish to have inside of the range, right? So here, when we print a equals to, do you remember string formatting, right? With string formatting, you can call upon the dot format, and then you reference the array that we've created, okay? And then we can display it in terms of a string by using the curly brackets and the index number 0, because we only have one variable in this code block, isn't it? So here we can see that upon running, right, you would find actually the resulting array indeed has 1, 2, 3, 4, 5, 6 elements, right? So we specified that we wanted 6 elements, which starts from 1 and 10. So the values 2.8, 4.6, 6.4, and 8.2 are actually, they're equally spaced within one to another. So from 1 to 2.8, 2.8 to 4.6, and so on and so forth. Python, or more specifically NumPy, using its built-in method called linspace, has very nicely done the calculation for you to create an array with 6 elements between 1 and 10. These are the linearly spaced number values that we have. It's 1, 2.8, and so on and so forth. Okay, so another function that is quite similar to linspace or linear spacing is called arange, right? Instead of specifying the number of elements between the start and end positions, with array range, we need to specify a step, right? So as we can see here in this code block, this example, we are using the array range from NumPy. We specify the first number, starting value. We specify the end value, which is 10. The step size is actually how much of an increment is between the first number, second number, and so on and so forth. So here we specify the step size of 1, so it's going to increase by 1 at every step. Okay, so as we run this, yeah, you've seen the answer. Well, line number 6 is the answer. You would find that actually, instead of specifying how many elements we have inside here, right, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the end value, it doesn't really, if you remember correctly, using the range function, the range and the number at the end, the end value of a given range, it always ends at the given value. Say it's 10 here, it's always -1. So you would find that actually, even though you specified 1 until 10, the range is going to, the resulting array is going to end at 10 minus 1. So if you want the array to end at an even number 10, you would have to change the arange to 11, right? So let's see how this goes. You'll find that actually, yeah, it goes from 1 to 10 thanks to the slight change here that we have with the arange. So I'm not going to change anything that's from the textbook because it's not really my prerogative, it's someone else's book. I'm just here as somehow I could say, yeah, I'm an instructor trying to deliver the message within the textbook, so I don't really have the liberty to change anything. Okay, so like I said, when we run this again, you would find that the answer is actually like what we see in line 6, right? Starts at 1, ends at n value minus 1, so ends at 9. So don't be surprised if it ends at 9 because ranges usually work that way. Okay, so moving on. We just hit the 30-minute mark, so if you feel like all of this is a bit overwhelming, you can pause the video and then take a mini break and then come join me again when you're ready. Okay, but as for me, I will move on because this is a single take recording. Okay, so anyway, the next subchapter is actually how to retrieve and erase dimension and the data type. Right, so when we need to retrieve information about a pre-existing array, NumPy offers several methods. The built-in methods are called ndarray.ndim. So this is actually useful for us to return the number of axes of the array. And then ndarray.shape, it returns the dimensions of the array as a tuple. So it returns the number of elements in each axis, x and y. And the ndarrays.size, actually it returns the total number of elements in each axis. And last but not least, ndarray.dtype returns the data type of the elements of the array. Okay, so say we have a 2x2 array. So it's a multi-dimensional array, but a small array nonetheless. Okay, as usual, we import NumPy as np, and then we use the dot array to define the array. You can see with the multi-dimensional list, with the multi-dimensional array, you have double brackets, double square brackets, because the first bracket is actually to somehow signify that actually this is a multi-dimensional array, and inside the array you have two separate lists. Okay, so 1, 2, 3, 4. So when we print out all of these built-in methods that we have here, so let's try to identify them one by one. Okay, I'll comment this out. Okay, so print a.ndim. So we want to find what is the number of dimension. So when we print out a.ndim, you would find that it's actually a 2-dimensional array. And then in line 8, I'm printing out a because I wanted to see the array when it is printed out as an array produced by NumPy. So you would find that actually the array is 1, 2, 3, 4. Okay, so next we could find out what is the shape. So the shape is actually 2x2, so it has 2 columns and 2 lines. Like previously we had 2 lines and 3 columns, that's 2, 3. Now we have 2, 2, which means we have 2 lines and 2 columns. Okay, so that's the shape. What is the size? So the size actually tells you the number of elements in each axis. So we would find that upon printing it out, we would find that the number of elements. Yeah, so the size is actually 4. Okay, and then let's go see the data type. Obviously, this is going to show you the data type. Shows you integer. Integer 32. I believe it's called 32 bits. Yeah. And if it's float, it's 64. So the memory allocation is a little bit different. Oh, integer 64. I see. It's no longer integer 32. Okay, so times have changed. So this is indeed an integer 64, not integer 32, right? A is composed by integer 32 type objects. Well, actually, Colab tells me it's integer 64 now. Well, apparently, due to the advent of very fast-moving technology, it seems that our code is now interpreted as integer 64 type object. So basically, if it's 64, it means it's one of the various integer type objects provided by NumPy. Well, the 32 or the 64 actually tells you what is the bit size of the integer. So this, what we have here, is actually a 64-bit long integer. So, well, as civil engineers, you don't really need to worry about the bit sizes, because we don't, well, respectfully speaking, we don't really deal with terabytes of data. Well, not yet anyway, because civil engineering data is very expensive. Therefore, we might not have a lot of it, but if you know how to process it, then it becomes very valuable to us. So don't worry about memory allocations, because we don't really deal with so much data unless you are dealing with image classification data, and then that's a whole other story altogether. Okay. Alright, so moving on. How to access and modify the elements of an array. So NumPy arrays are indexed starting from 0, like lists, right? Because you have the first position, you have index 0, second position, you have index 1, and so on and so forth. However, in NumPy arrays, the syntax used to access a certain value within an array is slightly different. How different? We'll see it in this following code block. Okay, so in this example, we have this NumPy array. So we have 2.45, 3.75. So it's a very small array indeed. Okay, so because it's a 1D array, it's enough for us to just specify is it 0 or 1, right? Because when we say a in square bracket 0, it is easily understood that we are referring to the first position or the 0 index number. Okay, so let me very quickly comment this out, and I want to see what happens here when we have an np.array 2.45, 3.75. And we have, oh, it's not going to give you a printout. Why? Because apparently I have disabled line number 5. I'm not supposed to do that. Okay, so what happens here is we have an array that we initialized 2.45, 3.75. And in line number 4, we have reassigned 2.45 to become 16. However, when we print out a at position 1 or index number 0, it shows you 16.0 because the original data type is actually a float. So when you assign an integer to it, it will still save the integer and convert it to a float instead. So let's see what happens when we print a. So after line number 4, you would find that actually the array would look like 16.0, 3.75. Sorry, 16 point, there's no 0, and then 3.75. As usual, when you pass the list and you make it into an array, the array doesn't show comma in between, so it's a nice representation of the array, looking very nice. Okay, so line number 3 to 6 is finished. So let's move on to the second array, which is B. Okay. So here we have a 2 by 2 array, right? So notice that when you are trying to specify the position, previously you had to use double square brackets, but then in terms of NumPy arrays, you just need to specify the position by doing this 1 comma 1, because it is when we need to retrieve a value, or when we are assigning a value, as we are seeing here in line number 8, we specify the position of the element using only one set of square brackets, because 1 comma 1 is actually referring to the I and j, right? For lists, the same operation was made using the following syntax, right? I and j. Previously we did this, the double square brackets I and j, but then with NumPy arrays, the I and j can be within one set of square brackets instead of two. Okay, so be careful not to confuse both, right? Because if you use this, you need to be wary that actually the use of one set of square brackets to define the I and j, you can only use it in conjunction with NumPy. However, if you're using lists, you would need to use the double sets of square brackets. Okay, we can also change the value stored at a certain position of the array, for example this line here, right? So we have 0 comma 1 2 comma 3. Okay, so I'm actually curious how B looks like before. Sorry, I need to delete this. So I'm curious to see what B looks like if we print out B before we assign the value of 28 inside of our new newly modified array. So previously we have B, which is 0 1 2 and 3, but then B is at 1 comma 1 is actually 28. So when we print B in square brackets 1 comma 1, it's going to show you 28, right? And then you can see that at index position 1, so the 1 is actually referring to the second line, and this j is actually referring to 0 and 1. So the first one, the first number 1 here, the index, is actually referring to which row, and the second index number, it refers to the element inside the second line here. So used to be 3, but then now it's changed to 28. Okay, so now that's done. Let's move on to mathematical operations between arrays. So we are creeping up to 45 minutes in probably a minute or so. Okay, so please bear with me. Mathematical operation between arrays, I think this will be handy, especially since you're taking vectors and matrices in calculus. So I hope that you'll be able to benefit from this new skill of yours. Okay, NumPy performs mathematical operations between arrays in an element-wise fashion. So what this means is actually all the arrays must have all the same number of elements inside them, otherwise it will show an error. Okay, so the next code cell, this code cell beneath, shows some of the possible operations that can be performed between two equally sized arrays. So we have we are missing something here. Import this always happens, doesn't it? Import NumPy as np. Yeah, story of my life. Everything in, okay, as. So we import NumPy as NP, and we define two arrays which are A and B. So A is 1, 2, 3, 4, B is 2, 4, 8, 16. Okay, so we can actually perform certain types of what is this? Summation of A. Okay, so print A plus B. Let's do this. It becomes, the new array becomes 3, 6, 11, and 20. Okay, so let's see the second one. Print A minus B, so it becomes negative 1, negative 2, negative 5, and negative 12. Yeah. Okay, so yeah, I think you can catch the drift. Let's see. For the remaining operations, A times B, this is going to be huge. Right? 2, 8, 24, 64. And then you can do some we did some multiplication. Let's do some division. And I have a feeling what we will have here in line number 9 is going to be huge, because we're raising everything to, well, not really. If we are raising the B array to the power of to the power of 2, it'll be huge. So notice that when we divide integers, it becomes float, isn't it? Okay. So it become 149, 16. And let us see what is the, well, line number 10 is actually a bit special, because we are calling upon NumPy. NumPy's built-in method, which is called square root, and we pass the list, the array B inside. See what happens. That is where you will have the square root number. So you have 1.414, and then for square root, the square root of 4 is 2, square root of 8 is 2.828, and square root of 16 is 4, right? So everything is in floats. Okay, I forgot where this came from. I think this is, yeah, some Excel stuff I did. I'm sorry. So I'd really like to delete this, but then yeah, Google Colab is a little bit weird when it comes to text editing, so I'm just gonna, so please ignore it. Okay, so people have used Excel before might have noticed that the operation in line 3, 1, 2, 3, okay, so line 3 is actually the A plus B. It is similar to summing one column. Oh, actually summing two columns of summing one column of a spreadsheet, yeah, to perform the matrix product instead of the element-wise multiplication. Well, actually, isn't it? Oh, I see. So actually, line number 11 apparently is referring to this line here, print A plus B. Okay. To perform the matrix product instead of the element-wise multiplication, okay, so this is something new. We have to use the at instead. Or, old school people call it alias. Instead of the normal multiplication symbol, which is the star, right, as the multiplication symbol. So when you have here, so in this code block underneath, we have the example of mathematical operation between arrays, between the array A and B. So you have equally sized arrays, 2 by 2 arrays, 1, 2, 3, 4, and then you have 2, 4, 8, 16, right? When we want to multiply, when we want to perform the matrix product between A and B, you use this line here, print A at B. Okay, so it will yield this result here. So yeah, so it's very nifty like that. You were using NumPy to do the element-wise multiplication, which otherwise would take some time if you did it by hand, right? But please don't do this to check out your please do this method if you are trying to figure out, or you're trying to do double checking on your final answer. It still is very important for you to learn how element-wise multiplication works, yeah, because it's in your syllabus. Okay, so this is just an extra method of you checking out your final answer. Okay, so please 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 do that. I hope it helps. Okay, so I think we're almost done here. There's a part here which I won't specifically go into very deeply. Why? Because it's actually calculating internal forces of a beam using NumPy. So when we calculate internal forces, this, I promise, will belong to another video which doesn't have to do anything with your test one, I promise. But then I will release this video, don't worry. Just not in conjunction with the test one, right? Okay, so I think 1, 2, 3, 4. Yes, so we have 4 code blocks left, and we are hitting the 50-minute mark. It'll be over soon, I think. Won't take longer than 1 hour 30 minutes. Okay, so please bear with me. Now we've arrived at array slicing. What is array slicing? It's used to perform operations on certain parts of our given array. Okay, so this next code cell, which we can see here, it shows some slicing types of operations for one-dimensional arrays. For example, when you have here, like we previously did, we have a linearly spaced array that starts with 0, ends with 10, and we wanted 11 elements, right? Which means it starts with 0, ends with 10. Because we're using linspace, the second number after the starting number that you specified, this number 10, will definitely show up in your range, right, in the end product. However, if you're using array range, the second number, or the number in the middle, it has to be this number 10 minus 1. Okay, so please be wary if you're using linspace or arange. Make sure you know what is going to be the output. If you're using linspace, the number at the middle is actually the number represented in your range. However, sorry, in the array. However, if it's arange, this number here has to be deducted with 1, right? And you won't see number 10 here if you're using array range, just like ranges, right? So here np linspace 0, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So indeed we have 11 elements, right? So when we print a, this is what is shown, okay? But let's see when we enable line number 4, what happens? We are slicing to 5, okay? What does this mean? Let's see what this means. This means we are taking in line 4. So we can use semicolons to print only the elements between a starting point and an ending point of an array. So you can see here, if it's 2 semicolon 5, it means it starts with 2, 3, 4, but when you specify 5, it's supposed to end with 5, but it only shows the number before the ending. So which is why you can see here, when we slice the array 2 semicolon 5, it only shows you 2, 3, 4. So say I want to change the slicing to show us the numbers between 4 and 8, right? So what I should do is I should change this. Probably it'll be nicer if I did a new line. Okay, A The double typing strikes again. Okay, so A, and then I wanted it to start with 4. Then I wanted it to end with number 8. So I should specify after 8 is 9. So I should put in 9 because I wanted it to end with 8. So let's see. Is it 4, 5, 6, 7, 8? Yes, 4, 5, 6, 7, 8. Because I specified the starting and I specified the ending. Minus 1 becomes 8, right? Therefore, I should choose the number 9. Okay, so last but not least, let's take a look at what is the printout at line number 6. What happens? A, and then I specify 1 to 8 and then 2. What's going on here? What's the deal? Okay, so let's just print it out. See, it's showing here 1, 3, 5, 7. What does this mean? Okay, so in this line, number 6, because I have several extra lines here just to show you very clearly what the array looks like and what multiple versions of the slicing looks like. Okay, so for this last line here, the syntax 1 semicolon 8 semicolon 2 means we take every second element between second element of A between the positions number 1 and number 8. So between number 1 and number 8, we take the every second element, which is why we denote 2. So this is the starting, this is the ending, and this is the step size. Okay, so when we have 1 until 8, but then we take every second element, which means we print out 1, we print out 3, we print out 5, and last but not least, we print out 7. 8 is not included because after 7, the second element is actually 9, and it's actually out of our specific range 1 to 8. So we only print out 1, 3, 5, and 7. Okay, so I think this is going to be as hard as it gets. 1, 2, 3. Yeah, so 3 more. So for multidimensional arrays, the syntax is the same, except each axis of the array can be sliced independently. Okay, so array slicing for multidimensional arrays also follows the same syntax. So let's just see how this goes. Usually we import NumPy as NP, and then now we have this massive matrix. It's an array, a 4x4 array, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So when we print it out, we can see that it's actually, this is the matrix that we have, a 4x4. Okay, so I'm going to show you several different ways of slicing, okay, with its corresponding notation, so that you have a better understanding of what's happening. Okay, so now in line 4, we've fully seen the matrix that we are working with, so that we can do a quick comparison when we are slicing it, where exactly does the slicing happen. Okay, so when we print matrix and then we have a semicolon here, comma 2, okay, so let's just run this. So this means we are selecting all lines using the semicolon. Okay, so which means lines number 1 until 4 is actually selected, which is why the semicolon is at position I. So at position J, we specified 2, right? So 2 is actually referring to the index number of the column. So the index number of the column starts with index 0, index 1, index 2. So when we specify 2 here, it actually refers to the third column for all lines. Therefore, the resulting printout actually just shows you, it's just all lines, but then it's just focusing on this column here, the third column. Therefore, you'd have a resulting printout of 3, 7, 11, and 15, as we see beneath here. Okay, so that is line number 5. Okay, what happens if we use the semicolon on the J part of the I and J specification of slicing a certain matrix? Okay, let's see what happens in line number 7. So similar to our example previously, right, it selects all of the columns because the J part is the one containing the semicolon. But we have the number 3 here, which is the index number 3, which means that we are actually referring to the final line, right? Since we have 4 by 4, which means this is index line number 0, index number 1, index number 2, index number 3, right? Since all of the columns are included, but then this line, this number 3 at the position I, it refers to the final line or final row of the given matrix. Okay, so similar to line number 5, right, it selects the 4th line of the matrix, which is the bottommost line of the given matrix. Okay, so just now we had the 3rd column, now we have the 4th line. Excuse me. So last but not least, let's go and take a look at example which is written in the final line. Sorry, line number 8. So what this is showing us is actually this line displays the 3rd and 4th column. Okay, when we specify the I as 1, right, we are actually selecting line number at index number 1, which is, this is line index 0, line index 1. So let us zero in on this line only. So we have 5, 6, 7, 8. Okay, and then we specified 1 semicolon 3, which means we wanted the index 1 up until 3, but not including 3, right? Because when we specify this with the semicolon 1 semicolon 3, we start off with index number 1, 2, 3, but ultimately it excludes the element at index number 3. So the output would be 6 and 7, as you can see beneath here. Okay, so as we can see here in this notation, or in the notes that I've provided, well, the ones that I got from the textbook anyway, the previous code cell, notice when slicing the semicolon, NumPy cuts the array from the starting position to the ending position excluded, right? So in the case of 1 semicolon 3, you have 1 index number 1 to 3, but it's number 3 is excluded, so basically it's just 1 to 2, right? Index 1 to index 2, 6 and 7. This is why line 5, oh, this is why line 5, the previous code cell, oh yes, okay, is it this one? The previous code cell, well, we have several previous code cells, but yeah. This is why line 5 of the previous code cell does not give an error, even though the index 4 is out of bounds, okay, for an array with 4 columns, right? Probably this is in the textbook. But then, yeah, you need to, even though you specified an index number that is out of bounds, because it only extends to, when you specify a starting position and the ending position, even though the ending position is out of the range, this is not causing an error because the ending position is excluded and you would have to subtract the ending position with 1. Therefore, it doesn't produce any error, okay? Because arrays are always indexed from 0. Yes, again, my very liberal use of exclamation marks is just an indication of me being excited. I'm not shouting at you, okay? Don't worry. So yes, towards the very end, I'm also still very excited because we have 2 more code blocks to go. Okay, so this, I promise, isn't going to be very, very difficult. Okay, so array union and concatenation. You have the horizontal stack, or H stack, and you have the vertical stack, which is V stack. Can be used to merge 2 or more arrays together. Okay, so the array union, we have 3 types of arrays here. So we have A, which is 1, 1, B, which is 2, 2, C is 3, 3, so on and so forth, right? So let's just see what we did here. We are trying to show what is the difference between a horizontal stack and a vertical stack. Right, for line number 5, the horizontal stack, you call upon the NumPy's horizontal stack method and you specify what are the arrays that you would like to stack together. So here we have carefully chosen A, B, and C together. Okay, so remember you have double round brackets. Okay, so in order to see what it looks like, let's just run this code. Okay, when we print out the horizontal array, that is, yeah, so this is horizontal stacking. So it goes from one side, so it's from 1, 1, 2, 2, and 3, 3. So it is in one horizontally stacked line. Okay, so what happens when we stack it vertically, right? So when we print out vertical and we use the V stack instead of the H stack, see what happens. So we're stacking 1, 1 on top, and then it's followed by 2, 2, and 3, 3. And so the stacking is from top to bottom. So the very first array that you specify will be the topmost one, and the last array in the V stack would be the bottommost one. Okay, so that's just one point to remember. Okay, so yeah, last but not least, we are going to see the append and insert before we end things, before we end the lecture today. Okay, so append and insert is just like our list previously. We can use both functions or methods to add new elements inside a given array. Okay, so say we have an array A again, np array 1, 2, 3. Okay, so when we print out the first iteration of the array A, you'll find it's just the 1, 2, 3, the original array that we have. Okay, so what happens when we append 4 to it, right? Try to print it out so you'll see the difference. Previously it was 1, 2, 3. Now when you append a 4, it will be added towards the end. It's the last element of the new array. Okay, so what happens when you insert A, 2, 7? What happens? Right, so this is something new for insert. The append adds an element at the end of an array, so you can't really specify where it's going to be added. It's always going to be the very last element, right? The latest addition to the element of your array is always at the end when you are using append. However, when you use insert, we add an element at a certain position, so it's no longer just towards the end. Okay, so what we have here is we have the A, which is the array, and then you have 2 and 7. So the second argument of the insert, so this is the second argument. It can be an iterable object, for example a list or an array, which specifies more than one position where to add the element specified by the third argument. Okay, so both append and insert take the optional argument axis used to specify the axis along which the operation must be performed, but then in this case we'll just use the normal insert function. Okay, so with A, comma 2, comma 7, what happens? So a comma 2, comma 7 tells NumPy to add a new element, which is 7, at index number 2. So index number 2 is usually referring to an element at position 3, right? So you have index 0, index 0, index 1, index 2, which is why this number 7 appears in the middle of our array out of nowhere, and it pushes number 3 and number 4 to the subsequent index numbers. Okay, so that is the difference between append and insert. Therefore, that concludes our chapter 3, NumPy. So there's going to be several more chapters remaining, specifically 3 more new chapters. After this, we'll be looking at computer algebra systems, CAS, right, in which you can actually take the variables inside of a given algebraic expression, and then you can apply certain mathematical operations or methods onto it. Yeah, you know, like you can take a mathematical expression and you can do some derivation or some integration on it. So we will look at that a little later. Okay, so we have chapter 4, chapter 5, chapter 6. This is chapter 3, which means that we are almost halfway through the entire semester. So thanks for joining me for the past 1 hour or so, and I hope this helps with your code along. I'm sorry if I spoke too fast. You can always slow down this video if you want. And all the best. If you have any questions whatsoever about NumPy and you have trouble trying to install NumPy library, right, feel free to contact me or text me. Yeah, please text me during office hours, or you can leave me a message at Schoology so then I can help you out. Okay, so this is me signing off. All the best, and I'll see you in chapter 4. Thank you and good night.